Hi students, welcome to my lectures on designing of non-ideal reactors. And before I start the lectures, I request you people to follow the lectures from the beginning. Because every lecture is connected. So this is whole idea of non-ideal reactors. If you know kinetics, RTD and mixing models, all three are required to design non-ideal reactors. That means to predict the conversion in the non-ideal reactor. Presently, we are at these positions and residence time distribution analysis. In residence time distribution analysis, we are into understanding the concepts of residence time distribution curve, cumulative curve, mean residence time, variance and skewness. By taking a specific tracer curve experiments, we have found out how to draw the E of t graph, how to draw F of t graph. So let us move ahead to find out the mean residence time, variance and skewness. The other names for the mean residence time, variance and skewness. Normally, the mean residence time is termed as first moment of residence time distribution, and the second moment of residence time distribution is given to the variance, and third moment of residence time distribution is called the skewness. These gives a certain information about the non-ideality in the particular reactor using the tracer curve experiments. Let us find out the mean residence time, variance and skewness in this lecture. What is mean residence time? Okay, you know, we are performing the tracer curve experiments to find out the E of t, F of t, mean residence time, all the things using a injector where you are going to inject a pulse of the tracer. So the pulse of the tracer will move along with the reactants. At the end of the reactor, we are measuring only the tracer molecules using titration methods or some other methods. So this is how we are performing the tracer curve experiments to find out what is the non-ideality in this mixture. The blue one is the regular reactants. The red circles are our tracer which mixes along with the reactants. So it will give some information about the time. This is what the whole agenda of tracer curve experiments to find out the non-ideality in any reactors. So today we are going to discuss about the mean residence time. The mean residence time means don't get confused with the regular reactants. The mean residence time we are trying to find out for the tracer molecules, how long the tracer molecules on an average stay inside the reactor. That is what the mean residence time. There is another time you already know, which is called the space time, which is volume of the reactor by volumetric flow rate of the reactor. So this is called tau. Okay, this is for the reactant molecules, and tau, Tm, which is we are going to find out using tracer curve experiments, the mean residence time of the tracer which have injected into the non-ideal reactor. So these both are different, that is Tm and tau is both are different. So please don't get confused. And we already know the E of t graph. Okay, from the E of t graph, we can able to find out the average time spent by the tracer molecules in the non-ideal reactor. So we already know that different molecules spend different amount of time. So that time information we can get it from the E of t graph. As you can observe, the A1, that means there are certain fraction of molecules spend time between 0 and T1. There are certain molecules that spend time between T1 and T2. Similarly, T2, T3, T3, T4 and T4, T5. So every molecule, every fraction of molecules spending different amount of time. So there must be some average of tracer molecules that spent in the reactor. So the average time spent by all the molecules in the reactor is called the mean residence time. Okay, which is also called first moment of RTD. So how to find out the mean residence time? It is very simple formula. Mean residence time based on averaging methods. It is written as mean residence time is equal to integral 0 to infinite t into E of t dt. So you can check the units. The time has the units of minute. E of t has the units of 1 by minute, and dt has the unit of minute. So ultimately you get time. So evaluating this particular integral, you can able to find out what is the average time spent by all the molecules. So only if this behaves as an ideal reactor, that means this reactor which drawn as a circle, which is a non-ideal reactor, if it behaves as a ideal CSTR or ideal PFR or ideal packed bed reactor, then the mean residence time will be equal to the space time, which we are going to prove it at very later part of the lectures. So let us evaluate. That means if you have done the tracer curve experiments in this particular reactor, that is non-ideal reactor, then what is the average time spent by the molecules we are going to evaluate. So mean residence time is 0 to infinite t into e of t dt divided by integral 0 to infinite e of t dt. This is the formula, but we already know that integral 0 to infinite e of t dt equal to 1, because area under the E of t curve will be equal to 1. So let us move ahead. Let us find out the mean residence time using a sample data, that is tracer curve experiment data. That means people might have injected, people which have injected some amount of tracer, and at the exit with respect to time they have got the E of t graph. From the E of t graph, let us evaluate the mean residence time. So let us find out the problem. Find the mean residence time of the reactor using pulse RTD data, the time information, C of t information, E of t information. How I got the E of t information? If you follow my earlier lectures, I have got through time and concentration information how to get the E of t information. So if you can able to read through the example, you can able to figure it out how I got 0.152, 0.457, 0.302 and so on. So let us find out the mean residence time of all the molecules. Is the time is up to 0 to 5. So integral 0 to t5 t into E of t divided by integral 0 to t E of t dt. I know area under the E curve, the complete area under the E curve is 1, which is a fraction. The fraction of all the molecules will be equal to 1. Therefore, mean residence time is equal to integral 0 to 5 t into E of t dt. Now I have to apply the integration formula, that t into E of t is my f of x, dt is equal to dx. I normally show everything, every time I show this integration formulas, if it is a 2-point formula, 3-point formula, 4-point, 5-point, 6-point, I apply this particular integration methods to evaluate the integration. So using this method, I have 6 points here, 0, 1, 2, 3, 4, 5. Automatically 6 points are there. So I use the 6-point integration formula to evaluate that my t into E of t is my f of x. Okay. So let us find out what is t into E of t. I know t. I know E of t. If you multiply t into E of t, I get another number. So like that, at different times, t into E of t information I can able to get. Using this t into E of t information, you can use this particular integral, and I get the value, the mean residence time equal to 2.22 minutes. That means few molecules enter at time t, exit at time t equal to 1, few molecules exit at time t equal to 3, few molecules exit at time t equal to 5. So on an average, all the molecules exit at a time which is a mean residence time of 2.22 minutes. So this is how the mean residence time can be evaluated given the t, C of t, E of t and t into E of t information. Okay, so let us move ahead to the next part of the story, variance. Variance. The RTD, which is also called residence time distribution of second moment. Okay, what is exactly variance? That means if you have some sample data, it could be data 1, it could be the data 2, it could be data 3. Imagine all the 3 comes from the 3 different non-ideal reactors. So everyone has a different spread. You can imagine the RTD of a non-ideal reactor, which is represented by 1, has a little spread. If you take the 2 RTD of a non-ideal reactor 2, you have a more spread. Okay, RTD of a third reactor, even more spread. That means the RTD information, even though the mean residence time of all the 3 reactors are the same, but the spread is different. You can see the 1 have a lower spread and 3 have a higher spread. Okay, the variance is something talks about how much is your spread of your RTD data. Okay, more is the variance, more is wide is your curve, less is the variance, shorter is the variance of the curve. So let us say variance sigma square, it is represented by sigma square, indicates how the fraction of molecule distributed around the main Tm. So this is the Tm. The distribution of the non-ideal reactor 1 is less. The distribution of the non-ideal reactor 3 is broader and shorter curve indicates large variance. Broader, that means you can see very broad curve. The red one you can see very, okay, peak. Okay, it's a peak, and it's a highest peak have a lowest spread. Broader in the sense, I have represented it where, okay, it's a peak, high peak. Okay, high peak and short, you can see the spread is short curve. Indicate large variance, which means there are fraction of molecules that come early as well as very late. I'm sorry, this one is represented, it's not a broad. Okay, sorry, I've just mistaken. The blue one is the broad one, which has the short peak. The red one has a you can see very high peak, that broadness is very less. That means broader and short curve. Take the example of the 3. It's called broader curve and short curve. Indicates large variance because very large deviations. That means there are molecules which wanted to come early and there are molecules which wanted to come late. Okay, that means in the reactor there are short-lived elements and there are long-lived elements. So this is called the measure of the spread. Narrow and sharp, you can see these are narrow and sharp curve, which is called the red one. So narrow and sharp curve indicates that the most of the fraction of molecules come near the mean. That means almost all the molecules which entered the reactor wanted to exit at the same time around the Tm. Okay, that means you can see it is called a narrow and sharp curve. Okay, broader curve. So this is how low sigma square, that is called plug flow behavior. That means in the plug flow reactor all the molecules will come at the same amount of time at the reactor exit. So the lower value of sigma square is indicating the plug flow kind of behavior. The higher variance is indicating because once the reacting molecules enter the reactors, heavy mixing is happened. Because of the heavy mixing happened, and all the molecules will have because there are molecules which wanted to come early, there are molecules which wanted to come late. So two reactors with the same Tm will behave differently if one having a different value of variance than other. Take example reactor 1 and reactor 3. The reactor 1 and 3 has the same mean Tm, but reactor 1 has very low variance and non-ideal reactor 3 has a very large variance. That's what this indicates. The two reactors with the same Tm will behave differently if one having different value of variance than other. What is the use? It is used to quantify, that means the variance term is used to quantify the flow non-idealities, and based on these experiments we can able to design the reactor, we can modify the reactors so that make sure that most of the molecules spend same amount of time in the reactor. So it is also helps that what sort of problems is reactor is facing. It's also help in predicting the performance. So this is what the broad use of sigma square. Variance give some information about the non-ideality in the reactor. So let us see one example that how to do. Find variance for a pulse tracer. That means imagine there is a pulse input that is happened. That means you have inputted some amount of pulse. So the tracer molecules are also gone into the reactor, and there is a detector. It will measure the how much amount of molecules that is coming out along with the regular reactants. Okay. So based on this particular experimentation, I know with respect to time how much amount of concentration of tracer molecule exiting the reactor. So at 0 time no molecule comes out. At time 1 minute 2 gram per liter of molecules is detected in the exit. Like that, I have the information. So similarly, based on time and concentration, the tracer concentration information, I plot E of t data. That if you refer to my previous classes, I have figured out how these values of E of t have come. So if you immediately in this particular lecture itself, I have explained based on the given data, the average molecules time of the molecules spent in the reactor, that is mean residence time of the tracer molecules, is 2.22 minutes. So this is the formula that we are supposed to use to find out variance in the tracer data. Variance can be calculated by integral 0 to 5, which is data is given up to the 5 minutes in of t minus tm square into E of t dt. So tm is given, which is same for all the data. The t is changing 1 minute, 2 minute, 3 minute, 4 minute, 5 minute. So based on that, now this is my function. What is my f of x function? T minus tm whole square into E of t dt. So let us find out at different times what is the value of f of x. Simply by plugging the value of E of t multiplied by t minus tm whole square, you get the f of x information at different times. So you apply the integration method, integration formula. How many points are there? 1, 2, 3, 4, 5, 6 points there. You can use the 6-point formula to find out what is the variance. The variance which have got is 0.687. Okay, this or the variance in this particular tracer curve experiment data comes out to be 0.687. So degree of residence time of the molecules around the mean. That means you have found out what is the, on an average, what is the variance of the tracer curve experiment, which is around the mean, which is called 2.22. So this is how we can able to figure it out, how much amount of variance is in this particular data. So let us go to the third moments, which is called the skewness data. Skewness. I mean, we were discussing about the mean residence time, which is first moment, and it comes to the variance, which is second moment. Now it comes to the skewness, the third moment of RTD, which is residence time distribution. So how to calculate the residence time distribution? There is a particular formula comes up, that is x cube is nothing but 1 by sigma 3 by 2 0 to infinite t minus tm whole cube into E of t dt. So what does this skewness indicate? If you have a skewness indicates the measure of extent that distribution is skewed in one direction. Example, you can observe these two figures. What you have observed in the particular figure, the most of the comes are you can see the tails. The tail is towards the right hand side. Okay, you can see the curve is bent. It's just like a bent kind of, most of the molecules are towards the zero. That means if you see a tail, that means there are majority of the molecules that exit the reactor at the early time, and there are molecules that is still coming out of the reactor at a later time also. The tail is towards the right hand side. Okay, that means a majority of the molecules spending less time, majority of these molecules exit the reactor at very early time. So that is why the peak is towards the left. And observe this right hand side. What is the skewness? Towards the left. That means the peak is towards the left hand side. What this means is majority there are molecules, few molecules which want to come at the early time, but majority of the molecules you can see come at the later stage. So this is called skewed towards the right and skewed towards the left. Skew, that means if S cube is positive, that means whatever the value we are computing, the value is getting positive number. That means you get a skewed towards the right hand side. If you get a number negative, that means it is skewed towards the left hand side. That means skewed is if tail is of the curve is towards the right, that is positive. If tail of the curve is towards the left, that is called negative. Okay. Negative and positive, you can see the recirculations and back mixings. That means I'm just trying to figure out, you can see for this particular case, you can see there are dead zones. I mean, for example, there is a non-ideal reactor. Inside there are kind of dead zones. Okay, because of this dead zone, majority of the molecules, recirculation back mixing. If there is a stirrer in the reactor and which is trying to rotate, the molecules at a very high speeds, kind of, what happens, because every molecule is rotated at high speeds and mixing, proper mixing happens, you can able to get this kind of different curves. If there is a bypassing happens, okay, this kind of bypassing can be noticed with this kind of skewness. From the skewness, variance and data, you can able to figure out what kind of non-ideality is happening in the kind of non-ideal reactor. We will discuss the things at the later stage, that how the curve looks like when if it is kind of recirculation, how the curves looks like if it is a bypassing. In future we are going to discuss about it. Right now, how I hope you understand, there is a term called skewness which gives the tail curves data. So let us do the small example to find out the skewness. I know because find the skewness for a pulse tracer data of a reactor. That means there is a reactor, people have conducted some tracer curve experiments. From the tracer curve experiments, you get the data of time versus concentration. From the time versus concentration graph, you get the E of t, which we have discussed in the earlier lectures as well. So from these examples, in the present example, I have already told you, I have already shown you that how to compute the value of mean residence time, which is 2.22 minutes, and what is the kind of variance, which is 0.687 minutes square. That is sigma equal to 0.687 power 1 by 2. Done. And based on this information, let us plot E of t and skewness data. What information required to plot the skewness? You can see the skewness formula is given by SE cube is equal to 1 by sigma power 3 by 2 into t minus tm cube into E of t dt. Now my f of x function in the integral is t minus tm cube whole cube into E of t. I know already t, which is called time data. I know tm, for every value there is a mean residence time of t 2.22 minutes. The E of t information is also provided. So I can able to compute t minus tm cube into E of t. So I know t, I know E of t, I know t minus tm whole cube into E of t. I get the informations. Once I get the information, right, I use the integration formulas to compute 1 by sigma power 3 by 2 into 3 by 8 and adding up of all the data based on the formula I have shown. So finally I got skewness is equal to 0.2. Skewness I got the 0.2, which is the tail is towards the right hand side. That means majority of the molecules come at the early stage, and there are molecules in the reactor which come at a very late stage. Okay, thank you. Let us move ahead for the next lecture.